Okay, so let's get started. Welcome everyone to the second seminar of our BERD, that represents our Biostats, Epidemiology and Research Design fall seminar series. We had our first talk 2 weeks ago, and we're having our second talk today, given by Dr. George Agogo, who works for the CDC in Kenya as a senior statistician. Before I formally introduce him and we get the presentation started, we'll run through a few of the logistics. This seminar is co-hosted by Professor Lan Kong and myself. My name is Terry Murphy, and we both work in the Department of Public Health Sciences here at the Penn State College of Medicine in Hershey. And I'm showing you now a slide that shows the 7 seminar presentations this fall. 2 weeks ago, we had Dr. Ajit Vemuri from here talking about wearables as adaptive interventions. Today, we're very happy to have Dr. George Agogo talking about some joint modeling of correlated cognitive function and functional disability outcomes. And it has a special statistical feature in that it is designed to accommodate bounded and missing data in a longitudinal study of aging. We meet every 2 weeks. You can see here the remaining talks. Our last talk of the fall will be on December 8th. This link here shows you the schedule and how to register. These are free to the public, and we welcome anyone who wants to come and join us. Here are a few of our logistics. This presentation is being recorded, so after Dr. Agogo's presentation finishes, at that time, we welcome people to unmute their mics and speak out and ask questions, but we do want you to know that it will be recorded and that later we upload this presentation to YouTube. So if the idea of your voice or your photo being on YouTube is disagreeable to you, then you are forewarned. We ask folks to mute their microphones. I see everyone is muted during the presentation, but you are encouraged to submit any questions or comments via the chat box. We will have Q&A at the end, and anyone who has registered will receive a copy of the slides, a link to the recording, the YouTube recording, and we will ask that you fill out a very brief seminar feedback survey so that we can continue to monitor and understand whether we're reaching the needs of the community with the talks that we're giving. So before I hand over the podium to Dr. Agogo, I will just state that I had the pleasure of working with Dr. Agogo at my former institution, Yale University, when he came there to do a postdoc in biostatistics from 2016 to 2018. And he has a PhD in biostats from Wageningen University in the Netherlands. He got that in 2015. He had a master's of statistics from Hasselt University in Belgium in 2011, and he did his bachelor's in math and computer science in Kenya. So he has, studied in 3 different countries, actually 4 different countries, including his postdoc in the US. And a lot of his work in his dissertation had to do with handling measurement error and finding ways to address that, something that we usually assume doesn't exist And so that's a great area. Another area that he has specialized in is in joint modeling. And joint modeling is typically you follow some continuous or count outcome, and then you also look at another outcome along the way, and you model them jointly so that they share information and inform each other. And this generally leads to less bias in the estimated associations of the explanatory variables with both of the outcomes. Now, as Dr. Agogo goes into his work, I do want to draw your attention again to the fact that this work comes out of aging research, where you often are modeling multiple outcomes, and they are correlated because they're both, in some ways, manifestations of what we think of as the death process, of our aging death process. In this case, he's modeling cognitive function and functional disability, and he's going to talk about what happens when one of the outcomes has boundaries, as many of the survey instruments do, and when there's missingness. And unlike, missing at random, which is the common assumption with most missingness, most methods of dealing with missingness, his approach specifically handles missing not at random. So it captures a lot of subtle things in statistics that are often ignored. And so it's a really rich area. So Dr. Agogo, I'm going to stop sharing and I'm going to hand it over to you. And once again, thank you so much for joining us today. Can you now share your slides, Dr. Agogo?
Yes. If you stop sharing, let me.
Yes.
And Terry, you let me know if when you're able to see my slide.
Yes, we can see your slides now.
Okay. So thanks Terry for the great introduction. And I also want to thank you for the opportunity to present part of my work that I did with my collaborators 2 years ago. And I also want to thank you for the clear introduction to joint modeling. I think that's a very nice preamble to the talk. And just to say is that this methodology is just one of the ways to model multiple outcomes, in this case, cognitive function and functional disability outcomes, which are very key for the elderly people, who are 65 years and above, because they are keen on their cognitive status. They want to be able to do things on their own, even as people become old, and also, things that are key to them, like dressing up, cooking for themselves. So those are things that are very important to the elderly people. Now, this talk covers key aspects of the resulting outcomes. Number one is the boundedness that we are going to see, where depending on the instrument that we are using to assess these outcomes, you find that values are restricted within a given boundary. And of course, because this is a follow-up study of elderly people, such studies are characterized by massive missingness, which we are going to see. Yes, so as I've just said, cognitive function, for example, cognitive decline and functional disability, are key health outcomes among older people. And these outcomes are often correlated. For example, you find that people who are cognitively impaired are also more likely to be functionally disabled. So there's that correlation between these outcomes, mostly in a positive way. So as one goes bad, the other also goes bad. So positive correlation in most cases. And they're also often associated with comorbidities, as well as demographics, or social demographics. For example, you find that cognitive decline is associated with advanced age, similar to functional disability. So we become less independent as we grow old. And to assess such the risk factors of such outcomes, we usually use longitudinal studies. So where we follow people over a long period of time to assess risk factors of cognitive decline, for instance, cognitive impairment, as well as functional disability. Now, as we've just said, and Terry clearly pointed it out, that because we are following older people over a long period of time, such data are characterized by massive missing data. People die along the way. Some of them are lost to follow up, or some just decide that, I don't want to participate in the study anymore. Maybe because of, old age, they are fatigued, and, so such things. And now, in aging research, especially when you want to look at the cognitive status, one of the instruments that is usually used is what we call the mini mental state examination. And so mini mental state examination, the MMSE, is basically a 30-point assessment tool that is used to test global cognitive function by examining key components. So we have orientation, registration, attention, language, and visual construction. So these 6 components, within each component, there's a series of subcomponents that sum up to 30 points. Terry, just to confirm, are you able to hear me well?
Yes, sir, I can hear you loud and clearly. If anyone in the audience
Thank
cannot
you.
hear, please tell us via the chat. Otherwise, we'll assume everything is copacetic.
Thank you, Terry. Now, this is an example of a MMSE tool for testing global cognitive ability or function. So for example, under orientation, you ask whether they're able to know which year we are in, the season, the month, date, and time. And if they spell those correctly, all of them, they get a score of 5. Also the country, town where they live, the district, the hospital, and the ward of law. If they get all correct, 5 points. The same with the registration. You ask the names, for example, examine the names of 3 objects. So if they, and ask the patient to repeat, if they can repeat all those objects correctly, they get the maximum score. The same thing with attention and calculation. So you ask them, for example, if you subtract 7 from 100, then you repeat the sequence for, let's say, 5 times. If they get the numbers correct, for example, 7 subtract from 100, you get 93. 97 subtract from 93, you get 86. 7 subtract from 86, 79. 7 subtract from 79 should be 72. So if they get all correct, they get 5 marks. And also you test the recall and the language. So if they got all these points, they total up to 30. If they don't get any, they get 0 score. So that's what is actually bringing in the boundedness of the MSE score between 0 and 30. And now, if you look at down here, I hope you're able to see, we have the scoring categorization here. So 24 to 30, that's someone with no cognitive impairment. Between 18 to 23, mild cognitive impairment. 0 to 17 is severe cognitive impairment. So this is a global tool. One thing that I really wanted to emphasize is that you might find that 30 people, you get people scoring everything. So that doesn't necessarily mean that they have the same cognitive ability or status. It's only that their score is actually restricted by the design of the tool. Okay, and also people scoring 0 doesn't mean that they have the same cognitive status. It's only that it's just due to the artifact of the tool that is being used here. And that's one of the aspects of this research where I want to show one of the ways to model such data. Now, again, I've said, so a person's MSc score can either be a perfect score of 30, we call it ceiling, because you cannot go beyond 30, even the design of the tool. So that's called the ceiling effect, or a worst score of 0, which is a flow effect. You can't go below 0, given the design of the tool. Now, if, for example, a given number of people score exactly the same marks, which is 30, it doesn't mean that these people are the same in terms of their cognitive status. And therefore, based on MSc score alone, you cannot actually differentiate these people, okay? Now, that's on cognitive function being measured using MSc score that is restricted between 0 and 30, and scoring a maximum of 30 or a minimum of 0 doesn't mean that those people they have the same cognitive status. Now, the second outcome here is functional disability. So functional disability is assessed using what we call the activity of daily living, okay? To do the following key essential daily self-care tasks. So it's when people usually like to be independent in such a way that they're able to walk by themselves, they're able to feed themselves, they're able to dress up, they're able to do toileting by themselves, they're able to bathe and to transfer or to move from transferring, for example, moving from their seat to the bed and things like that. So these are very key activities, especially for elderly people, because they need that independence. And if they need assistance with one of these key self-care tasks, then now we say they are disabled. So activity of daily living disability is defined as being incontinent or needing assistance in performing at least one of these key self-care tasks. So in this work or this presentation, so we have two outcomes. So that the cognitive function and functional disability. So they are both of primary. We consider them primary outcomes. So we want to look at the effects of risk factors on them simultaneously. Now, by the time when we were doing this work, we scanned through literature and we realized there were very limited research on how to jointly model correlated outcomes that are subject to informative missingness. So informative in such a way that the missingness pattern is informed by some characteristics that are observed and some that are not observed. And also flow and ceiling effects in, for example, when we're using MMSE score as a measure of cognitive function. So in the literature, you find that people have proposed methods to, for example, only account for the ceiling, but not the flooring, or the flooring, but not the ceiling. But in this particular work, we proposed a method to account for or to address both distributional aspects of MMSC score as a measure of cognitive function, while jointly modeling MSc score with functional disability. So functional disability here is binary. So it's either you're functionally disabled because you need assistance with at least one of these key self-care tasks. So it's either it's yes, no. So you are functionally disabled, yes, no. Therefore, we proposed what we call a shared parameter joint model to study risk factors of cognitive decline as measured by MMSC score and functional disability as measured by ADL disability, while handling the missing data because we are using longitudinal study where we monitor or we follow elderly people over time. And of course, there's a lot of missingness due to death, for example, and the flow and ceiling effects of MMSC score. And because these outcomes are also correlated, we also show how to account for the correlation between these outcomes, the two outcomes. Now, I will now go to a bit of statistics now. using this, a lot of notation, statistical notation, but I'll explain this in a way that you will not be scared with these symbols. So basically, we denote a health outcome. So health outcome is MMSC or ADL disability with this with YIJK. So Y is the outcome, I is just the person index, J is the outcome type. So whether it's one, if it is cognitive function as measured by mini mental state examination. Two, if the outcome is functional disability as measured by ADL, activity of daily living disability. K here, subscript K is the time point because we are dealing with longitudinal studies. So the time, the follow-up time at which the measurements were taken. So it can be in terms of wave, year, month, depending on the design of the longitudinal study. Now, then the Y bolded subscript IJ. So basically, this is just a way to denote a vector. A vector is just a way to compress or to simplify notation of multiple outcomes or multiple variables. So we let Yj be a vector of outcomes in the waves the ith person is followed. So basically what we do is just we represent outcome measurements for each person using a vector. A vector is just I can say is just basically just a way to represent a series of observations from a particular person or study unit. Then we partitioned that outcome vector into Yij superscript O to means observed and M for missing. So basically, so we have a series of measurements for a person. Then we want to partition it to the observations that were, the measurements that were observed and the ones that were missed over the follow-up time, okay? Then now, another notation here is the missingness indicator. So we want to see whether, basically it's a vector of 0, 1, 0, 1. So if the observation Yij was measured or observed or measured, we denote it by 1. Otherwise, if it was missing, it's denoted by 0. So R subscript IJK is basically, in short, is just a series of 0 ones that indicates whether the outcome was measured or missed, okay? Then now we talked about joint modeling. So joint modeling basically means that I have more than one outcome, but I want to model them simultaneously. So I want to model them together. And therefore, so here we have, what we have here on the left side of the equation here is a vector of the outcome. So superscript O means that they are observed, and the ones that were missing, and the R here is the missingness indicator. So 0, 1, 0, 1, whether observed, yes or no. And the theta here is just a vector of the parameters. So this parameters, theta here is, for example, if you want to see the effect of age on cognitive function. So all those parameters are under the vector theta here. Now, on the right side of the equation here, so basically what is happening here is that we are partitioning our outcome vector. So the first component here, F here, is just the probability density function of the outcome partitioned into observed and missing, and then the missingness pattern. So the second function here, density function here, is for the missingness pattern. Now the third density function here, the vector mu here, is now, these are the latent factors. So latent in the sense that these are factors that were not observed, but affects the outcome as well as the missingness of those outcomes. So that's the third component here. So The first component are the outcome observations, whether observed, outcome measurements, whether observed or missing. The second component, density function here, is the missingness pattern. And the third one is just the density function of the latent factors. So it's the integral. Basically, it means that we are integrating over the latent factors, because we don't have the latent factors on the right-hand side of the left-hand side of the equation, so we integrate them out. Now, the random effect. Now, this mu here is called the random effect. It captures the interdependency or the correlation between the outcomes. So in our case, functional cognitive function as measured by MMSE, as well as functional disability as measured by ADL disability, activities of daily living disability, and the missingness process. So the missingness process is captured with this, the missingness pattern here. So it's the second component of the density function here, function of Rij. So that one is where we model the missingness pattern explicitly. So the shared parameter framework postulates that there is an underlying latent process. So the unobserved factors that drives both the outcome measurement, so that drives both the cognitive function and functional disability outcomes, and the missingness process, and is appropriate under what we call missing not at random. So we have different missingness mechanisms. Number one is what we call the missing completely at random. So basically, it means the missingness is at random. So it's not influenced by, let's say, observed or unobserved factors. And then we have what we call the missing at random. So basically, if, especially in a longitudinal study, if the subsequent, the susceptibility of subsequent measurements to be missing are influenced by what was observed in the current wave or the current time point. Whereas the missing not at random means that the missingness, the probability or the susceptibility of missing outcome in subsequent visit or measurements is influenced by unobserved characteristics. So it's a very flexible way of modeling missingness. Now, under the joint modeling framework here, so I said we have different components. So we have the outcome subcomponent, the missing and the missingness component. So now, based on this presentation and this work, so we have the cognitive function subcomponent, we have the functional disability subcomponent, and we have the missingness subcomponent. So basically our joint modeling here, or joint model here, has three components: two outcome components and the missingness component. So now we have what we call the MMSE score submodel component for cognitive function as measured by mini mental state examination that is bounded between 0 and 30 and is assumed to be continuous. Now, for this particular outcome, because of the bounding effects, we assume what we call a mixed effect Tobit model. So Tobit model is able to account for the bounding between the maximum and the between minimum and maximum values, and we define uncensored latent MMSE score. It's latent in such a way that we don't observe it. So just to emphasize this, that we know that the actual, you find that people can score the same maximum value or minimum value. That doesn't mean that they have the same cognitive status. So there is that random variability or heterogeneity in those people who score exactly the same points, minimum and maximum. So basically, this is how a Tobit model is defined. So it's a mixed effect in the sense that it has the fixed effects component. So that is what is denoted by the the beta transpose X. So X vector here basically means is the covariate effects that are measured. And these are the covariates. X are the covariates of the risk factors that are measured, and the beta is their effects. Now the second component here now captures the latent. So what is not observed, okay? Now the mu here are the latent effects or the random effects, and C vector here just the design matrix of those latent effects. And then the last component here is the random error term. Now we assume, because this is a vector representation, we assume that the mu I here is multivariate normal. So it follows a normal distribution. And also that the error term here, the random error term here also follows a normal distribution. So basically a mixed effects topic model assumes a random normal distribution for the latent MSC scores. Yeah, so topic regression models assumes a normally distributed MMSC score censored at the lowest value, which is the floor, and also the ceiling, and the development between the floor and ceiling over time. So now we've talked about the latent MMSC score and what we are observing, okay? So we assume we can observe the latent MMSC score for a given range of what we are observing between 0 and 30, okay? It means that what we are observing here, so we are relating what we are observing, the Y without asterisk, and the latent, which is the Y with the asterisk. So this equation, let it not scare us. What it basically means that what we have here, so the Y is what we are observing, and the Y with the asterisk is the latent, the true, but unobserved. So the minimum values denoted by L here refers to all MMSC score values that are less or equals to the lowest, the least value. And what is observed and the latent refers to values that are between the floor and the ceiling value. So any value that is greater than 0 and less than 30, so those, what we are observing, we assume that those are the same as the latent MMSC score. And any value that is 30 and above basically refers to, so basically it means that all MSC score that are greater than 30, we kind of trim them back to 30. That's what it means. So whenever we assume 30, it doesn't mean that the true MMSC score is 30. It's only that we are trimming them back given the artifact of the tool. So that's one of the limitations of this tool. I'm not able to see the top here. Let me see. So sorry, there's a part here that I'm not able to read given this. But so the second component is the functional disability, is the functional disability submodel as measured by ADL disability. So this is binary. So if a person needed assistance with at least one of those 6 components, then we say that person is functionally disabled. So it's a binary yes or no. So for binary outcomes, we usually use what we call the logistic regression, okay? Where we model the probability or in terms of odds ratio. So the odds of something happening over the odds of something not happening. Now, so it's a mixed effects because we have both the fixed effects, covariates, which we are observing, denoted by this vector W, and the latent, denoted by the latent factors, the mu, but with a vector, design matrix vector, sorry, the design matrix here, denoted by V. Then the last component of this joint model is now the missingness component. If you can recall that the shared parameter denotation where we had the three components, the outcome, the missingness pattern, and of course the latent component. Now, this would have been very complicated, but we decided to simplify it a little bit. So we assume the same missingness pattern for cognitive function as measured by MMSE score, as well as functional disability as measured by ADL. And again, because it's either the observation is whether the outcome is observed yes or no, it's also another binary outcome. And similarly, we use a logistics mixed effects regression model here. So the missingness process and the two longitudinal outcomes, they share this mu. So these are the mu here are the latent factors that or influence someone's outcome, and also whether it is observed yes or no. And then now the lambda here quantifies the association between the probability of missing longitudinal MMSE score and or ADL disability and the underlying latent factors. So the underlying latent factors are the mu's. And that's why we use actually, we are say that shared parameter is a shared parameter because we are sharing the latent factors between the outcome as well as the missingness pattern. And it's because of that that we thought that this method is appropriate for modeling data that I'm not missing at random. So here, we call this model the joint Tobit model. It's a joint Tobit because we are jointly modeling the two outcomes and the missingness pattern. But of course, we are using Tobit to model the continuous component, which is the MMSE score. Now, so that's the theory of the joint modeling, but usually it's good to apply these methods in real life where you are faced with a given research problem and you want to address it. So now we are using the Chinese data, Chinese Longitudinal Health Longevity Survey that began in 1998, where they interview oldest old, so 80 years and above, in a randomly selected counties in 22 provinces in China that are representative of the Chinese population. And then they were followed up and recruitment of new samples were performed in the year 2000, 2002, all the way to 2014. And for this particular work, so from 2002, there was addition of adults who was 65 years and above. So for this particular work, we used data for about 16,000 participants who participated in 2002 wave. So we consider 2002 as baseline, and then we use subsequent years as follow-up. And then now here, we measure cognitive function using MMSE score and functional disability using ADL's disability. And then as covariates, we just assumed age, sex, and education. This at baseline. So age at baseline, sex, education at baseline, and systolic blood pressure. Then now, usually, once you apply your method to a real data set, you also have to assess how your model performs. And that is usually done by a simulation study. So simulation study is basically a way of generating artificial data that mimics real life study design, where you assume that you know the truth and you estimate how far off your estimates are based on your method from the truth. So I think because of time, I'll just skip through this. So basically, did a simulation by mimicking this Chinese longitudinal healthy longevity study using the parameters shown below, where mu1 are the unobserved factors that underlie a person's susceptibility to cognitive decline and ADL disability, and mu2 are latent factors that underlies a person's susceptibility to missing outcomes. Again, we simulate MMSE score following Tobit distribution and ADL disability following logistic regression. And then now, again, so then we fitted a joint Tobit model, what I've just discussed. And the second one is, I call it joint normal distribution. So basically, I assume instead of Tobit distribution for MMS score, assume it is normally distributed. And I wanted to see how that assumption impacts the estimates. And then, of course, then you measure the accuracy of your estimates, effect estimates. So using what we call relative bias, which is just the difference of what you've estimated and the truth divided by the truth. And then the empirical standard error, which is the standard deviation, the parameter estimates from multiple. So basically in a simulation study, you generate multiple sets of data, and in each set you fit a model and estimate the parameters of interest, and then you come up with a series of estimated parameter values, and then you can summarize. Now, this is a histogram of MMSE score from the Chinese data, and you can see the bounding at 0 and 30. That is, and then we did this for each of the waves. And then now, of course, in this table here, we are characterizing the missingness. So for example, we see a lot of missingness here between wave 2002 to 2005. Those who are lost to follow-up is about 12.6% in the first wave. Then by yeah, so those who are lost to follow-up were 2012 in the first wave, so that is about 12.6%. By the end of the wave, 2014, there were only 114 who are lost to follow up. No, sorry. So between 2002 and 2005, 2012 were lost to follow up. Between 2011, 2012 to 2014, 114. But basically what this means is that if you look at, by the end of, if you can focus attention in the last column, you see that by the end of the study, there were only 10.4% of the participants still alive. A whooping 84.5% either died or were lost to follow-up by the end of the wave. So that's a lot. Now, if you look at, for example, the MMSE score, the first wave, we only had about 51% of the observations. By the end of the wave, there were only 10%, 10.2%. So there's a lot of missingness here. The same for ADL disability. Between wave 2002, between 2002 to 2005, by 2005, we only had about, again, 50%, 51%. And at the end of the follow-up, we only had 9.93% observation. So there's a lot of missingness there. Now, so we fitted the joint model assuming Tobit distribution for MMSE. Again, also joint model now assuming normal. But if you look at this, so the outcome, this is the effect of age, female sex, the follow-up, wave, education, and SBP. If you look at the effect estimates here, we see that actually the effect estimates are sensitive to the distribution assumption for the MMSE score. And we see that actually by assuming normal distribution, the effect estimates are attenuated, so they are smaller in size when you assume a normal distribution. And some very key observation here is that for the ADL disability, we don't see much differences. So the joint modeling here has more effect on the continuous outcome. And also because for the ADL disability, we assume logistic mixed effect. So it doesn't actually impact, the estimates are not impacted much, whether you assume Tobit or normal distribution for the cognitive function. And again here, under the missingness here, we see that advanced age, follow-up time, and education here, and increased blood pressure increases the susceptibility of missing observations or missing outcome in subsequent waves. So that's what it means here. So a negative value here means that increase in those risk factors increases the susceptibility to missingness in subsequent waves. I see we have 12 minutes to go. Now, these are the results from the simulation study. So for the simulation study, we also see that, again, we see that if we assume a normal distribution for MMSE score, the effect estimates are less precise compared to when you assume a Tobit distribution. So relative bias here is almost close to zero for all these risk factors when you assume a Tobit distribution for MMSE score, but the bias is quite substantial when you assume a normal distribution. Again, the effects are not very profound for ADL disability, which is a binary outcome. So from this, we can say that the joint modeling of MMSE score for cognitive function and ADL disability for functional disability and missingness reduces bias in the effect estimates of risk factors that is attributable to dropout or missing note at random. And that we saw from the simulation study. And now from the real data analysis, so from this Chinese data, we saw that if we ignore the floor and ceiling effects of the MMSE score, the effects estimates are impacted substantially. So we saw even they are attenuated, even masking the significance of some risk factors and attenuating. So attenuating basically means that the effect estimates are biased towards a null value of no effect. And also their standard errors are also underestimated. And we can say that the results underscore why it is very important to correctly handle missing data, especially in longitudinal studies of health outcomes that are correlated, as shown here by substantial bias in the simulation study for the effect estimates that when we incorrectly specify the models in the simulation. So I've quickly rushed through the results because of time, but here is the reference. So we published this paper in 2022 in behavior research methods, and there are quite a lot of work that are presented in that paper. And because of time, I was not able to explore everything or to present everything. And I would encourage that if you want to know more about this work, you can look at this reference. Thanks, Terry. Back to you.
Great. Thank you so much. I don't see any questions in the chat at the moment. I do encourage anyone to write their questions in chat, or if you feel comfortable, feel free to unmute your mic and speak directly to Dr. Agogo. I'll make a few comments. I think everyone listening is familiar with multivariable regression, and they're familiar with the idea that if you add confounders as explanatory variables, that helps reduce the bias in the estimated association between, say, your exposure, explanatory variable of primary interest in the outcome. This is a different way of getting to that same end, of getting unbiased associations. But what it does is it harnesses the longitudinal information of more than one outcome as they change over time. And the way I like to think of it is that shared information between the two outcomes that is not directly represented in the explanatory variables is captured in these shared random effects. And so it may seem a little intimidating to hear a talk like this, but it builds upon a lot of basic conceptual statistical ideas that all of you have probably seen before. I think to me, what's really interesting is you have a continuous model for the MMSE outcome, but instead of normal, George is introducing the TOBIT, which handles the censoring at the floor effect, the minimal value, and the censoring at the maximal value that's called a ceiling effect. He introduces another random effect that describes the likelihood of a certain outcome being missing. And as he showed us in one slide in the Chinese longitudinal study, by the time you get to the end, following old folks, you're down to about 10%. You see in those observed outcomes, you have about 10% in MMSE and ADL disability. So the part, George, that really intrigues me is the MNAR. Last year in November, I gave a talk in the same seminar, which was a brief introduction to missing data methods. And, what we usually do is we find a way to justify the missingness as missing at random. And then we either employ multiple imputation or we, often use mixed effect models for a given outcome. And assuming missing at random, adding the random effect often kind of interpolates. It takes care of the missingness and the outcomes. I wanted to hear your perspective on the other thing we often teach about missing not at random is that you have to clearly understand the mechanism of the missingness. Missing not at random is often conceptually thought of as the reason they're missing the value is because it's related to the value that they would have reported. So I wondered if you could just say a few words to us about how you think using this logistic model of an indicator of whether the outcomes are missing, how that captures, the missing data mechanism, and how it also captures that idea that their missingness is actually related to the possible values of the outcomes that they might have reported if they were present.
Thanks, Terry. Yeah, so I think I would just start by saying that as much as I know, based on my knowledge scope, there is no formal way to test for missing not at random and missing at random. There's no formal way. But one thing that is being proposed in the literature is to do sensitivity analysis under MA and under missing not at random. And just look at the effect estimates, whether the effect estimates are sensitive to the assumptions that you're using. Now, to your question on if I got you well, is including random effects when you fit a logistic regression. So just for clarification, Terry, in this logistic regression, is it for the outcome modeling or for the missingness?
Well, I'm thinking of your binary indicator of the missingness. Because
Okay, so so for this particular work, because if I can go back to the it's this one, right?
yes, equation 4.
Equation 4. So the question is, if we add, can you please clarify again?
Sure,
Mm.
just at a very high level, people often are scared away, or they try to avoid doing anything about missing data that is missing not at random,
Yeah.
because the common assumption is that to address that properly, you have to have some detailed understanding of the missing data mechanism.
Yes.
And the nature of missing not at random implies that the reason it's missing has something to do with what the person might have reported, usually bad results, like.
Yes.
So I just curious, where that fits in this model. Is it in the
Okay. Yes. So I got you, Terry. So now, if you look at these submodels for the missingness, we have this mu here,
Mhm.
and the same mu is also part of the functional disability submodel component, and the same mu is also part of the functional, the cognitive function component here. So these are things that are not observed, but maybe because they are bad, that people just did not want to report them, or
Sure.
they can be part of the variables, especially in a longitudinal study. You find that we don't measure everything. Maybe it's the genetic component of a person that was not observed or measured during this study. So we assume that there is a universe of those unobserved factors that we think influences whether the we will take measurements from these particular participants in the subsequent follow-up. So we assume that in addition to what we've observed, like gender, sex, age, education, and wave, there are other things that we did not observe that we think are likely to influence whether we are going to observe these people or not. And
Mhm.
that all those things, we lump them here under the mu. And that mu is shared across the three components of the model. Now, this lambda here now quantifies the effects of those latent things that we did not observe, but we think may influence the outcome, whether they are observed or not. So this is explicit here. So we are explicitly modeling the missingness here, because Terry, if we get rid of this third component, then basically we're assuming a ma, right?
Okay.
Yeah, but if we include, because we're explicitly modeling the missingness pattern under the assumption that is influenced by what we're observing, so the vector of z here, and those are the things that are latent, and that's the shared parameter component that are latent, but we think may influence somebody's outcome to be measured in the subsequent follow-up, yes or no.
Okay.
I don't know whether that answers your question, Terry. But of course, there are different ways to, I think there are, of course, pattern mixtures and those other methods that can also be used to model this missingness under missing not at random.
Yes. Okay. Well,
Yeah.
that's a nice kind of overview.
I think in the paper, we also looked at, actually, yes. So Terry, in the paper, I did not present this because of time, but in the paper, we also model the outcome under Ma assumption. Yes. So we also did that. So by assuming Ma, so basically when we drop the third component and see how the results are affected by that. So
Okay.
yeah. So, but
Oh,
of course we can
that's a
use,
great idea.
so another thing I think, Terry, and then if, for example, so the value of lambda here is, I think it was about 6 something. So it was very significant. If you go back to the results. So this lambda, this one here, it's very significant. No, a value of 6 and the confidence interval does not contain 0. So it means that actually those latent factors do influence the outcome in subsequent waves. But I'm just thinking now that you've raised this, assuming that this lambda value was very close to 0 or not significant, then I think we could conveniently assume Ma, right?
Okay. Okay,
That's
sure.
my thinking, yeah. Because
Okay.
joint modeling is very complicated. So if we can simplify the model and end up with more, almost the same effect estimates and the precision, then the better. Go with the parsimonious model.
Great. Well, George,
Yeah.
we're a little over time. It's 2:03. So
Yes.
we want to thank you for a really nice presentation, and we really appreciate your clear, slow explanation of the conceptual pieces. As it's clear, joint modeling is very complicated because you're combining several different multivariable models. You're estimating them simultaneously with this shared random intercept, which in this particular case is informing the 2 different outcome models as well as the missingness model. And in this case, it's assumed to be missing not at random. So it's very sophisticated statistical work. And we thank you for making us aware of this and helping us think through it.
Thanks so much, Terry. And I also want to thank the audience for taking their time to listen to this talk. And in case of any questions, please feel free to reach out, and I will be happy to address them. Thanks, Terry and the team.
Thanks so much, George, for staying up late after a long workday. George is, in a time zone where it's about 9 o'clock at night. So thank you so much, and I hope you sleep well after this.
Thanks, Terry. Thanks a lot for the opportunity also to present this work to your team.
Okay, we'll talk soon, George. Okay.
Thanks. Bye.
Thanks again. Okay, bye.
Bye, Terry. Bye.
Bye.